So we have a little bit left to go in section 3.3. We've been graphing parabolas, and we've looked at what to do if our parabola is given in vertex form, where we can predict the vertex with the shifts, left, right, up, down, and so on. And then standard form, where we have to work a little bit harder to find the vertex because we have to use that vertex formula. And the third form that we've talked about for quadratic functions is our factored form. So what happens if you're given a quadratic function in factored form and you would like to graph it? The short answer to that question is really you're going to have to multiply it out and use the same technique as for standard form. However, remember when it comes to finding the zeros, right, when I set this equal to 0 eventually, the factored form can really come in handy there. So it has a bit of an advantage, bit of a disadvantage. Let's take a look. So here I've got a function given to me in our factored form, and the first thing I want is the vertex. I'm going to have to multiply this out, otherwise I won't be able to use the a and the b and the c for my vertex formula. So when I multiply, I'm going to get x squared plus 7x plus 2x plus 14, or x squared plus 9x plus 14. That's my f of x, or I can also call it y. And now using my vertex formula, x would be negative 9 over 2 times 1 minus b over 2a is negative 9 halves, or negative 4.5. To get the y value, I'm going to take that value and I'm going to plug it back in to my original function. So I'd have negative 4.5 squared plus 9 times 4.5, 9 times negative 4.5 plus 14. In this case, I'm feeling pretty comfortable using the decimal, since the decimal and the fraction are exactly the same. If the division had not come out evenly, then I probably would have used the fraction here so that I didn't have inexact numbers going out. All right, let me just pop that into Desmos for us here. What is that? Negative 4.5 squared plus 9 times negative 4.5 plus 14. Okay, fairly large number here. Oops, maybe not. I missed the 9. It's 4.5 squared plus 9 times negative 4.5 plus 14. There we go. So it's negative 6.25. And just remember that if you wanted a fraction over here on the side, you could change it to a fraction, negative 25 fourths, but it comes out exactly, so using the decimal is really no problem. All right, so there's my vertex, negative 4.5, comma negative 6.25. I'm going to go ahead and plot that right away. Negative 4.5, negative 6, and just a little bit more, negative 6.25, both there. All right, axis of symmetry is that vertical line through the vertex. It's going to be here at negative 4.5. So x equals negative 4.5. All right, let's go for the zeros and x-intercepts next. And here we're setting y, or f of x, equal to 0. And here we actually kind of have an advantage in the fact that it was already in factored form, because when I set that equal to 0, I don't have to do very much work to solve that equation, right? Anytime I've got a factored form equal to 0, either x plus 2 equals 0 or x plus 7 equals 0. And I get x equal negative 2 and x equal negative 7. Those would be my zeros. I can turn them into x-intercepts by making them points. We know the y value is 0. So let's put that information on our graph. Negative 2 and negative 7. All right, one more algebraic thing to find, and that's our y-intercept. For this, we have to set x equal to 0. So y would be 0 plus 2 times 0 plus 7. 2 times 7 is 14. And, whoops, 0, 14 then is my y-intercept. All right, I have a couple choices here. If I just want to stick with what's actually showing on the graph, I could potentially just not plot that at all, since I already have the 2 points in addition to the vertex that I need. Or if I do feel, hey, I really would like to plot it, I could always say, I can kind of guess that would be 10, 11, 12, 13, 14, and I can just kind of extend it myself. If I do that, I do have the advantage of being able to use symmetry, right? This is 4.5 to the right of the vertex, so if I went a half, 1.5, 2.5, 3.5, 4.5 to the left, there'd be another point about there, symmetric to that y-intercept. And I can draw my graph. Let's see, I have to really judge this one to get all the way up there. There we go. But again, I didn't absolutely need that point, since I did have the 2 points in addition to the vertex that I really need to draw the graph. All right, domain, negative infinity to infinity. I know it's boring, but at least it's easy, right, for all parabolas. And then our range, we have a smallest y value here, which we know at the vertex was negative 6.25, and then we go up to infinity from there. Okay, in this one, the decrease comes first, right? We're decreasing, going downhill here until we get to the axis of symmetry, so from negative infinity to negative 4.5. Decrease. And then we increase after the axis of symmetry. We start going uphill, and that would be from negative 4.5 and forevermore out to infinity. So really I probably need to do one example of this, because the method of finding the vertex is exactly the same as finding the vertex in the standard form. In fact, as you saw, we had to multiply it out and get the standard form before we could find the vertex. The one nice advantage of factored form, though, is it makes it really easy to find those zeros and x-intercepts. Right? So that's a plus. Speaking of advantages, let's take a quick look back at the 3 forms and the kind of advantages, or what's easy to figure out in each case. Before I do that, I will mention, you all know, of course, that we do have Desmos, or a graphing calculator, that would graph any quadratic function for us. So you have a way of checking all this. But I will expect you to be able to justify all these features algebraically, like we've been doing in these videos. One of the really interesting parts now is that we can really begin to talk about the connections between the analytic forms and then the graph and how it looks. So let's think for a moment about the three forms that we looked at and talk about what were we really easily able to predict about a graph from each form. When we go all the way back to the first one, the vertex form. In the vertex form, it made it really easy to predict the vertex because we knew how the graph was shifted left, right, up, or down. So it was really easy to predict the vertex itself, probably why it's called vertex form. We also could predict whether the graph would open up or down, right, by the positive or negative on the leading coefficient. Now, if you remember the standard form, let me see if I can find one of those real quick. Something like this. It took more work to find the vertex. We had to use a formula. We could predict whether it opened up or down. Very quickly. And the other thing that was really easy from the standard form is that y-intercept, right? That last number, that c value, when you plugged in x equals 0, that's all you were left with. So really, getting the y-intercept was really, really easy with the standard form. These are things we can basically predict just by looking at them without having to really do any, written down, worked out algebra. What about our last most recent one, the factored form? When we had a factored form, the zeros, the x-intercepts were really easy, right? From the factored form, going to the zeros, you could have done that in your head. You didn't even really need to write it out, right? So the x-intercepts are very easy to find from the factored form. So all three forms have advantages and disadvantages. Some things are easier, some things take more work. Talk a little bit more about the open up, open down. Again, it's all about that leading coefficient. And this works whether you have standard form or whether you have vertex form, or if you have factored form, you can think about multiplying it out just enough to get that leading coefficient, right? If the leading coefficient is positive, it opens up. And if the leading coefficient is negative, it opens down. We did see that there's always one turning point. When the parabola opens up, our turning point is a minimum. And when our parabola opens down, the turning point is a maximum. But either way, there's just one turning point. Now, how many zeros does a quadratic function have? The quick answer that most people will give here is there's two, right? 2 zeros. But remember, there's one exception to that. Do you remember the graph that we did that only had 1 0? Let me see if I can find that for us. Most of them had 2 zeros, right? Most of them had 2 zeros, 2 x-intercepts. But the one exception to that was this one. When I found my x-intercepts or zeros here, set this equal to 0, I only got one result for the 0 and one x-intercept. In fact, when we graphed it, that x-intercept actually was the vertex. And that happens every single time. If there's only one x-intercept, it's because the x-intercept, or the 0, is right there at the vertex. So, as far as the zeros, usually 2, but we might only have one. If it occurs at the vertex. Now the zeros, remember, are very closely related to the x-intercepts, but they're not exactly the same. There's actually 3 possibilities for x-intercepts. Oftentimes we saw that we had 2, right? Something like this. If the 0 was right at the vertex, then we might have only had 1. Something like that. But you remember there was one other possibility? When our zeros were imaginary numbers, we actually had no x-intercepts, right? Never crossed the x-axis at all. So it's possible to have none. We could have something like this, where the graph never crosses the x-axis. So, how many zeros? Could be 2, could be just 1, but we might even have no x-intercepts if those zeros turned out to be imaginary. All right, we have one more kind of a new idea to talk about. I don't think we've talked about this yet. I want to talk a little bit about the end behavior of the graph. The end behavior of a graph refers to how the graph behaves at the far left and far right. Basically, what's happening at the ends after all the interesting stuff like the vertex or turning points or intercepts are kind of all done and accounted for. So let's talk about the end behavior of quadratic functions. The end behavior is different depending on whether my parabola opens up or opens down. If my parabola opens up, so maybe something like this, then both ends actually go up to positive infinity. So we would say the end behavior. To describe it, I would say it's up to the left, goes up on the left side, and it's also up to the right, goes up on the right side. On the other hand, if my parabola opens down, should use my space a little bit better, but we'll get through this. Then notice, instead of going up to the left and right, this one actually goes down to both the left and the right. And that again is how I would describe my end behavior. I would say it goes down to the left and also down to the right. As we describe additional types of graphs this semester, we'll see that it's not always true that both ends do the same thing. And so describing the end behavior is going to be one way that we can start to give a very complete description of a graph. All right, the last part of this section, we're going to start looking at some graphs, but we're going to try and go the other way. I have been giving you equations and asking you to tell me what the graph looked like. I'm now going to give us a graph and ask what we know about the function. So in example 4a here, here's a graph. I want us to say everything we can think of about this function. It can be about the graph pieces itself, or it can be about the actual formula that we would have used to come up with this function. So here I've got a parabola. And I'm going to start by talking about things that I can see graphically, and then we'll turn that into things that I perhaps know about the function itself, the algebraic representation. So graphically, let's just start with what we just talked about. This opens up, and so the end behavior is up to the left and right. What else can I read directly off the graph? Well, I can definitely see the vertex, right? It's right here at, what is that? -2, -16. Is my vertex. I can see the x and y intercepts. I have an x-intercept at -6, 0. And another x-intercept over here at 2, 0. And I have a y-intercept, looks like a 0, -12. So all of that is just information about the graph itself. I could add a little bit more that's maybe not directly drawn on, but that I can quickly figure out from the graph. We can certainly see where the axis of symmetry would be, right? Our axis of symmetry here would be at x equals -2. And let's see, I think maybe in terms of the just the graphical behavior, that might be a pretty good list. Now let's see what we can additionally say based on a formula. So what can I predict about the analytic function? I think I can predict quite a lot, actually. I believe that I can predict easily both the factored form and the vertex form. And from those, I could probably get to the standard form as well, although that would take a little bit more algebraic doing. Let's start with the vertex form. I've already seen that my vertex is -2, -16. So when I compare that to the origin, this has been shifted left 2 and down 16. Let's remember how our formula or our algebraic function would have said that. To go left 2, a horizontal shift left 2, I would have had to have had an x plus 2 squared. And then to go down 16, I would have a -16. Okay. Now I know that this opens up, so I know there'd be a positive multiplier. At this stage, short of actually multiplying this out and checking some points, I don't necessarily know right now whether there's like a 2 or a 3 or a 4 or something like that, or a 1/2 in front of this. But I think we can figure that out in just a minute or two. So let's just leave it at that for now. We know a lot about the vertex form just based on the left 2 and down 16. What about the factored form? Well, let's see. Because we knew the x-intercepts, we easily know the zeros. They're -6 and 2, right? In order to get those zeros, can you predict what the factored form looks like? Well, let's see. If x equals -6, wouldn't that have required a factor of x plus 6? That way when you set it equal to 0, you get -6. And similarly, to get a 0 of +2, I would have to have a factor of x minus 2. Again, when I then set that equal to 0 and solve it, I get the 0 of 2. So I believe my factored form is x plus 6, x minus 2. Once again, it's possible that there was a GCF factored out here. I don't quite know that yet. Right. So let's go ahead, and this one I have to work just a tiny bit harder for, but let's see if we can go ahead and get the standard or expanded form. Our third form. And all we would need to do is we could work from either one of these, right? Either I could multiply this out and subtract 16, or probably a little easier, I could just multiply this out. So if I multiply this, I would get x squared minus 2x plus 6x minus 12. Which is x squared plus 4x minus 12. This is where I can double check to see if there really should have been some multiplier there. Remember that the standard form, it's very easy to see what the y-intercept should be. Right? If you were to plug 0 in here, the y-intercept should be negative 12. And in fact, that's exactly what we saw in this graph. If that were not the case, this is where I would have figured out what multiplier I would have needed to make that y-intercept work. So I'm going to say, yep, in this case it just works, and therefore these two forms are also correct. I didn't need a multiplier. So we can predict and talk about a lot of things just based on a graph. We can list a lot of graphical qualities, but we can also often figure out exactly all of the forms of the analytic function just by looking at the graph. All right, we're going to try a couple more of those. And again, I'm going to begin by making a list of everything I can read directly off the graph. So this one opens down. I already know then that eventually my leading coefficient is going to have to be negative, right? My end behavior is down to both the left and the right. And let's see, what else can I say? I can say that I know the vertex right here is 4, 9. I can say the x-intercepts are 1, 0 and 7, 0. And the y-intercept over here looks like negative 7, so 0, negative 7. Let's see, what else can I say from the graph? Well, I haven't listed the x's of symmetry yet. We could do that. It would look like this. So x equals 4. Right? Well, you know, something I didn't do last time, but I could have. We could also list the intervals of increase and decrease from this graph, right? So if I wanted, I could say interval of increase, and this graph increases right away. It increases until we get to the axis of symmetry. So from negative infinity to 4. The interval of decrease would be the rest of this over here, right? So from 4 to infinity. And actually, I don't even think I remembered to list the domain and range last time. We could do that. Domain for the parabola is always going to be negative infinity to infinity. And my range goes all the way down to negative infinity, and the largest y value here was the 9. So tons of stuff, even more than I remembered to do last time, that we can write down just by looking at the graph with no additional algebra. Now let's talk about what else can we say about the analytic function. Okay, well, knowing the vertex is 4, 9, we know that this has been shifted, so let's start with the vertex form. This has been shifted to the right 4 and up 9. So my function in vertex form must have included x minus 4 squared, right? The horizontal shift is inside the parentheses, and then plus 9. I also know, because it opens down, there's going to be a negative in front of that, negative leading coefficient, to reflect it upside down. And there might be a multiplier in there. I'm going to leave just enough space to squeeze one in case I need one. I don't know yet. All right, let's go for the factored form next. Because I know what the x-intercepts are, I easily know the zeros are x equal 1 and x equals 7. So the factored form has to include an x minus 1. That way when I set that equal to 0, I'll get my x equal 1. And it also has to include an x minus 7, same reasoning, right? When I set that factor equal to 0, it has to give me x equals 7. Once again, because this is upside down, I know I'm going to have a negative leading coefficient, possibly a multiplier there, but I haven't got quite that far yet. All right, the last thing we need to do is this is the only place where we kind of have to work a little harder in terms of like working out some algebra. If I want the standard or expanded form, then I actually have to multiply out one of these. It doesn't really matter whether you multiply this one out or this one, but the factored form is usually a little quicker to work with. So I'm going to do that. I'm going to keep the negative in front of everything. And then I'm just going to multiply those two binomials together. X squared minus 7x minus 1x plus 7. And then when I distribute my minus sign, I'll get a negative x squared. That would have been a negative 8x, but because of the negative out there, it becomes a positive 8x. And then a minus 7. In this form, I can really quickly see that if x were 0, my y-intercept would be at negative 7. And that's exactly what I found. So again, I don't think I need to worry about any other multipliers other than remembering that negative that turned this into a parabola that opened down. So tons and tons we can say about this function just by looking at the graph. All right, I have one more. And again, we're going to start with the information just from the graph itself. Definitely opens up. vertex, I guess I didn't put a scale here on the x-axis, but if there is no scale, then you should assume that we're counting by ones. So 2, 4, -2, so on. So my vertex here would be at 1, 0. I could do the end behavior, which is up to the left and up to the right. And let's see what else we could put in the axis of symmetry. Which is x equals 1. The intercepts, this one only has one x-intercept, right? 1, 0. And notice that when there is only one, just like we saw before, it's right at the vertex. The y-intercept is here. Looks like 0, 3. Okay, let's see what else. We could do domain and range. Domain is just sort of a gimme, negative infinity to infinity. And the range, our smallest y value is 0, so from 0 to infinity. We could do our intervals of increase and decrease. Let's see, increase actually is over here. It goes up on this side, so from 1 to infinity. And our interval of decrease on this side where it's going downhill would be from negative infinity to 1. All right, I'm just looking through that. I can't think of anything else right now to say about the graph, but nice big long list there. So let's now see whether we can use what we see here to try to write an algebraic formula for this. Or several of them, actually. We'd like to see if we can write all the different possible forms. If I wanted to put this in vertex form, my vertex is at 1, 0. It's just been moved to the right 1. And that's it, right? It didn't get moved up or down at all. So I'm thinking y or f of x, either one, would be x minus 1 squared. Okay? I'm not adding or subtracting anything out here because I didn't move up or down. Now again, it's possible there's a multiplier there, but we'll find that out kind of as we go on. Factored form. Well, since the only x-intercept was 1, 0, the only 0 is x equal 1. And if you notice, x minus 1 squared really is a factored form, right? It's x minus 1 times x minus 1. What actually happened there is the x minus 1 really occurs twice. That 0 occurs twice. And again, I think this is a phrase we've used in the past. We see that 0 has multiplicity too. When that happens, that's something we'll talk a lot more about in actually the next chapter. So I just wanted to bring it up now, but that'll come back to haunt us a little bit later. At any rate, when you have a vertex form that's just no y values out here, the vertex form and the factored form are really going to look just alike. And then finally we have our expanded form. And that's the only one we kind of have to work for a little bit. I'm going to go ahead and multiply this out. So I'd have x squared minus 1x minus 1x plus 1, or x squared minus 2x plus 1. All right, as we've said, the expanded form is the one we can look at when we want to think about the y-intercept. And this, right now, would predict a y-intercept of 1, right? But that's not actually what happened on this graph. Our y-intercept was 3. So this is the only one that actually I actually have to worry about that multiplier, that vertical stretch. To make this go from 1 to 3, I have a vertical stretch of 3. So since the actual y-intercept is 3, I'm going to need a multiplier of 3 to get that vertical stretch of 3. And all I'm going to do is I'm going to go back and I'm going to put that in every single one of them. So I'm going to put the 3 here as a multiplier. That becomes my final vertex form. Again, here the vertex and factored forms are really the same, so you can either write it out or you can write it in its factored form like this. And I'll have to have that same multiplier then in my expanded form. So there's a multiplier of 3 here. There's a multiplier of 3 there. And my final expanded form then is going to look like 3x squared minus 6x plus 3. And now I've accounted for that y-intercept of 3 the way I needed to. All right, so hopefully in this section, I know there's a lot of stuff going on here, but working back and forth, not just from a formula to a graph, but also from a graph back to what you can predict about the function, graphically and analytically, allows you to really have a lot more flexible thinking than just going one way or the other. So, long section I know, but that finally brings us to the end of section 3.3.